Good evening, everybody. Thank you so much for joining us once again for the second of our Twilight CPD sessions in science. We are delighted to welcome back Dr. Neil Ingram of Bristol University, who is our team leader in science. And joining Neil are Ian Lovett and Barry Wild, lately of Ampleforth College and Cheltenham College, respectively. Neil heads the biology team, Ian the physics team, and Barry the chemistry team. So you're in absolutely expert hands tonight. The aim of these sessions is to support you delivering the new specifications for CE. And so this session is focusing on developing skills and topic focus, specifically thinking and working as a scientist. And later we'll also be discussing energy in the new 13+ science specification. This webinar comes as a sequel to our previous Twilight Science CPD session in March, in which we answered previously submitted questions in a Q&A with our wonderful experts. So I really hope you enjoy this session, and let me remind you to find us on social media. We are at ISEB Awards. We're on all channels, so please like us, be our friend. We just want to stay in touch. Once this session is finished, there will be time for questions. So please use the chat function in YouTube. Now, if you aren't logged into Google or YouTube, then you might not see that chat function there. So just have a quick look. And if you can't, Google or YouTube login will do that and unlock that chat function for you. You might also, if you would like to chat to us, create an account. So in order to get those questions across, just log in. You will be able to post any questions you like there during the session. Sophie will make a note of those questions, and she's going to ensure they're all answered in our Q&A later. So without much further ado, let me hand you over to Neil, Ian and Barry.
We're going to start with Ian's going to talk about energy. Just waiting for the presentation to come up. And then after that, I'm going to talk about thinking and working as a scientist.
Hello, I'm Ian Lovett. I'm, as Julia said, the team leader for physics for 13+ Common Entrance. So I'm going to outline the idea of the energy teaching in the new 13+ science specification. The next slide, please. So I'm going to have three sections to this brief talk. First of all, why we're having a change. Secondly, what the changed approach is. And thirdly, very briefly, some possible ideas for teaching strategies, or at least starting teaching strategies. Next slide. So first of all, why a change? Well, the teaching of energy has been debated often quite hotly for a long time. And that debate has influenced teaching methods, it's influenced textbooks and the national curriculum, which was first introduced in 1989. The idea of forms of energy, which are converted from one to another to make something happen, is appealing in its simplicity, but fundamentally incorrect. In addition, research shows that there is something of a disconnect between the everyday use of the term energy and the scientific understanding of the word, and that for many pupils, this causes problems in their understanding of what is a very important concept for all sciences. By changing the approach to teaching energy, we can reduce the likelihood of misunderstanding. Essentially, and scientifically, energy is a mathematical idea that allows work done to be quantified. Doing work causes something to happen, or perhaps alternatively, when something happens, work is done. In many cases, work is defined as force times the distance moved in the direction of the force. Energy is the way we quantify the work done. So in SI units, 1 joule is the work done when 1 Newton moves through a distance of 1 meter. So 1 joule is 1 Newton meter. That is the energy transferred between stores. The energy hasn't changed form. It's simply being transferred to another store because work has been done. However, we don't formally introduce the idea of work at Key Stage 3, so we concentrate on the idea of energy. And we can use the model of it as a quasi-material substance which is conserved. The idea of conservation of energy is one we can't prove at this stage, since we don't introduce the mathematical ideas behind energy at this level. But it is an idea that needs to be taught, accepted, and understood. The idea that energy is what makes things happen is also incorrect. Since energy is conserved, that idea doesn't make sense and reinforces an incorrect idea of energy being used up. In fact, of course, things happen because of a change in entropy, but we don't introduce the idea of entropy until much later either. So at Key Stage 3, it's reasonable to say that an energy store of some kind is necessary for something to happen. When anything happens that transfers energy, energy is transferred between stores in a way that leads to a more disordered system. For us, that is increased entropy. In other words, energy tends to spread out from objects or materials that have relatively large stores of energy, and that explains how things happen. In all cases, the energy is dissipated or spread out, and so becomes less useful. For example, if we have an isolated system all at the same temperature, no work can be done transferring energy from one store to another, and so nothing can happen. And you may be familiar with that as a possible scenario for the end of the universe, when everything becomes the same temperature, not at absolute zero, could be a high temperature, but because there's no temperature differences, no work can be done, no energy can be transferred, and so nothing can happen. The universe just sort of dies. Known colloquially as the heat death of the universe. Since we refer to stores of energy, it makes little sense to refer to the means by which that energy is transferred between stores as forms of energy or stores of energy themselves. If I push a trolley, causing it to accelerate, my chemical store of energy is being transferred to a kinetic store of energy in the trolley. We would not call my push a form of energy. And the same is true of electric current, of light, and sound. In each case, there's no way of defining or quantifying an energy store associated with electric current, or with light, or with sound. They are simply the mechanism by which work is done and energy is transferred from one store to another. Likewise, for a chemical reaction. So, scientifically, work is done when anything happens, and energy is the way we account for and quantify the amount of work done. Energy is not used up, it's a conserved quantity, but it is always spread out or dissipated whenever work is done. The mechanism for doing that work is not in itself a store of energy. New slide. So if that is the science, the physics behind the reasons for the change, how are we going to approach it now? So the new approach tries to deal with those inconsistencies which I've outlined and the inaccuracies of the previous approach, which used the idea of forms of energy. First, given that energy is a means of quantifying work done, we talk about stores of energy. And for clarity, we give labels to different stores. And you can see the list of the stores of energy on the screen there. New slide. Energy will be transferred between these stores when something happens, or more correctly, when work is done. Now we can define these stores in more detail, and you'll see the definitions there on the screen for a chemical store of energy, for a gravitational store of energy, and for a kinetic store of energy. Next slide, please. Things get a little bit more complicated when we talk about an internal or a thermal store of energy. You'll notice that I've put in heat and ringed it. And many of you will remember a time when heat was a taboo word, although heating, as we'll see later, is a pathway. Heat is usually defined as energy that is transferred spontaneously from an object at a higher temperature to one at a lower temperature, and so actually excludes work done. Work done and heat together make internal energy. Now, just to emphasize the difference, perhaps you can imagine you have a bicycle pump and you put your finger over the end and you pump the piston, and the air inside you can feel getting hot. You've done work on that to make it, to increase the internal energy of the air. You haven't heated it because you haven't transferred any heat from a warmer object to a colder object, but you have done work, and that increases the internal energy of the air. At sea level, however, it seems unfair to penalise the use of what is such an everyday word in pupils' everyday vocabulary when used to describe internal energy. So we will always put in our mark scheme, allow heat. All materials at a temperature above absolute zero have a thermal store of energy. And the temperature and the mass and the type of material all determine the size of that thermal store of energy. It is important not to confuse the internal store of energy with temperature, and I've seen this confused in one or two textbooks. Temperature is a measure of the mean energy of the particles in a material. Internal energy is the total energy of the particles in a material. So, to give you an example, a spark has a high temperature but a small internal store of energy. A bath of water, on the other hand, has a low temperature but a large store of internal energy. Now, I'm not suggesting that it's necessary to specifically make that distinction for common entrance, but by being aware, one can avoid any confusion. Next slide. Two more stores of energy: an elastic store of energy and a nuclear store of energy. Next slide. So we now come to talk about the mechanism by which energy is transferred from one store to another, and these are the pathways. And the pathways used at Key Stage 3 are mechanically, which means a force acting over a distance, which could be a push or a pull. It would include a sound or a water wave, heating, electrically, radiation, and a chemical reaction. In most cases, the pathway for an energy transfer isn't particularly important. All we're interested in really is from which store energy is transferred to another store. Next slide. So, for example, we might observe that a lamp connected to a cell lights up and emits light. That's a standard observation. Now, we can make an explanation of that by saying that the battery causes an electric current to flow through the lamp. The resistance of the filament causes it to heat up as the current flows and emit light, which we can see and which warms the surroundings. And notice in that explanation of what's going on, I haven't used the idea of energy transfers at all in a simple explanation of what is going on. However, We can analyze the energy transfers in that experiment by saying that the chemical store of energy in the cell is transferred by electricity to the internal or thermal store of energy in the lamp, which is then transferred by radiation to the surroundings, where it spreads out as internal energy. And in making those two statements, we've not confused our explanation of what is happening with an energy transfer analysis, or got mixed up with the idea of forms of energy. Next slide. So I'm not trying to go into great detail about how to teach energy. That, of course, is individuals' thoughts and ideas. But I think there are three key points that need to be brought out. First of all, an energy store of some kind is necessary for something to happen. Secondly, energy is always conserved. And finally, energy always tends to become more spread out or dissipated in any system. When anything happens that transfers energy, energy is transferred between energy stores in a way that leads to a more disordered system, or more dissipated system. In other words, energy tends to spread out from objects or materials that have relatively large stores of energy, and that explains how things happen. We might use a liquid as a model of energy spreading out from a large store to smaller stores, but at the same time being conserved. In the model, we imagine energy as an invisible, intangible substance that's the same wherever it is. The idea is that this model fits well with an understanding of energy as an abstract, quantitative and conserved property of a system. Next slide. So a simple example might be a ball moving through the air. When the ball is thrown, it moves through the air, colliding with air particles and making them move faster. This slows the ball down, and energy is transferred from the ball to many individual air particles. Another way of describing this is to say, or talking about the energy analysis, is to say that the kinetic store of energy that the ball has because it's moving is being transferred to the kinetic store of energy of the air particles. Now, a visual aid when teaching the example of the moving ball could be to have some liquid representing energy, which can be moved from a large beaker representing the kinetic store of energy of the ball to be shared between smaller beakers representing the energy stores of the particles. The energy in each store can be observed to increase or decrease. This property of energy stores means that they can be used to describe energy transfers qualitatively and to demonstrate clearly the idea of conservation of energy, since it can be seen that the total amount of energy, i.e. in our model liquid, doesn't change. And the same model can also be used to demonstrate that the act of sharing the liquid, i.e. transferring energy from one store to another, is not in itself a store of energy or an energy form. It's the mechanism by which the energy is transferred, and this is the pathway. In the case of the moving ball, it's a mechanical pathway, but in other models it could be light, electric current, or sound, or a chemical reaction. Next slide. When chemical reactions are involved, all the reactants and the products are considered as part of the chemical store of energy. So, for example, we might observe that a hydrocarbon is burned with oxygen to produce heat. In this case, the energy analysis is that some energy is transferred by chemical reaction from the chemical store of the hydrocarbon and the oxygen in the air to the thermal store of the surroundings and the chemical store of the carbon dioxide that is produced. Next slide, please. So when teaching energy, it's Robin Miller who wrote an article about teaching energy back in 2005. And it's been echoed since, that a good place to start the teaching of energy ideas is with energy resources, which include food and fuel. And this is an idea which we use that is important for all citizens, and especially now at the current time, and which all young people should be taught. And most pupils will know the word energy from their everyday language, from what they hear and what they talk about, and many will associate it with fuels and food. And it's better and perfectly correct to talk about using or consuming energy resources, but obviously incorrect to talk about using or consuming energy, because energy is a conserved quantity, and to talk about using energy can be confusing. And the idea that most jobs need a fuel of some sort to happen seems reasonable. So by emphasizing the idea of stores and pathways, the underlying principle that energy is a quantitative calculation of work done isn't compromised. We're not teaching it as such, but we're not compromising it either. And it should help all pupils to understand the concept of energy and energy resources without teaching incorrect ideas, which some will need to unlearn later on. So thank you very much. That's the end of my presentation. And I think we're going to have questions at the end.
Thank you, Ian. That's very, very impressive and interesting presentation. It's a good moment to emphasise that we have produced some teaching resources on key aspects of the Common Entrance Syllabus, one of which is about energy and which can be obtained from the new ICEB website. I'm going to completely change direction now and think about practical work and think about how we manage practical work in a scheme of work across several years. So when the presentation's ready, we'll begin that. Here it is. Thank you. Next slide then, please. My day job is to train science teachers on the teacher training PGCE course in the University of Bristol. And every year I ask my students, what is the purpose of practical work? And every year they say, fun. Practical work is fun. Practical work is engaging. Practical work grabs pupils' attention. And these, I guess, are the reasons why visually stimulating practicals such as the fiery hand, which I understand comes with health and safety concerns, so you want to check your risk assessments on that one, and the extraction of DNA from strawberries are key components of science courses for middle year pupils. But we need to get beyond the surface layer of fun and engagement to explore deeper reasons for undertaking practical work, which of course is both expensive and time consuming. And given the constraints on school budgets, we want the practical work that we do to be as effective as possible. Next slide, please. Now, one important report which came out in April 2021 certainly does go beneath the surface of practical work, placing it fully within the context of science and also the government's preferred pedagogy for teaching in what they call a knowledge-rich curriculum. And this is the report by Ofsted, which purports to be a research and analysis of science teaching. Although primarily aimed at the maintained sector, it's got a number of important ideas which could benefit the thinking of independent schools. And the report itself is available free of charge from gov.uk, and I recommend you all to go away and read and study it. Next slide, please. Now, this is an extract from page 6 of the report, which draws from a published research study that suggests that the reality of science learning for primary pupils in maintained schools is that it is superficially based on fun. but not on deepening the understanding of scientific concepts. Many studies suggest that pupils in the maintained sector felt that their primary school prepares them well for English and for maths, but not for learning science. And clearly this is something that we try and avoid and want to avoid in the independent sector. Next slide, please. The emerging pedagogy from the DFE is arguing for what they call extensive connected knowledge of science. This, it argues, is at the heart of scientific expertise. Extensive connected knowledge has an awareness of how ideas join together. It's not just a collection of randomly organised facts. And this has become the basis for Ofsted inspections of science departments in the maintained sector. We hope that our context-based questions that we use in common entrance exams do allow context-based teaching to take place, which does emphasise the connections between different parts of the syllabus and also between different subjects. And this is something that we'll explore a little later. Next slide, please. To go further then, the report makes the distinction between two different kinds of knowledge. What it calls substantive knowledge, which is the knowledge of the products of science, such as concepts, laws, theories and models. And disciplinary knowledge, which it calls the understanding of how scientific knowledge is generated and grows. And this is particularly focused on the working scientifically sections of the national curriculum. Next slide, please. Common entrance questions at both 11 plus and 13 plus are all context-based questions that may assess both substantive and disciplinary knowledge within the same question. In fact, we're busy at the moment reviewing the 23-24 papers, and I think every single question I have seen merges both disciplinary knowledge and substantive knowledge into those questions. You can't have one without the other. That's not to say there aren't questions there that only test substantive knowledge, but the discipline knowledge do have some content as well. Now, the equivalent of working scientifically in the common entrance we've called Thinking and Working as a Scientist, or TWAS. And at the present, it's very similar to working scientifically of the national curriculum, although we have simplified some of its requirements. And this is because working scientifically is the best model of disciplinary knowledge that is available probably anywhere in the world. It's certainly the best one that I've seen. And as schools work with us more carefully and extensively on TWAS, it could well be that in the future TWAS develops independently of working scientifically. We'll have to see. The reduction in substantive knowledge in the current curriculum is intended to allow schools to develop TWAS and disciplinary knowledge within their schemes of work. That is one of the major points of it. And it's important to realise that the two strands of knowledge are so intertwined that they cannot easily be disentangled. And for this reason, all the questions that we use in common entrance papers are rooted in one of the specification statements. I will never write a question about evolution, even if it's a disciplinary knowledge question, because evolution isn't part of the common entrance specification. Next slide, please. Now, one way to think about substantive and disciplinary knowledge is in terms of three broad categories: knowledge and understanding of science, substantive knowledge, and practical skills plus scientific inquiry, which make up disciplinary knowledge. Next slide, please. Thinking and working as a scientist is divided into four broad skill areas: modelling scientific attitudes, developing experimental skills, designing and carrying out investigations, analysis, evaluation, and problem solving. New slide, please. Some of these skill areas do contribute to the knowledge and understanding of science. For example, pupils need to be able to plot a graph, interpret a graph, and use it to draw scientific conclusions, each of which, of course, develops both the disciplinary knowledge and the knowledge and understanding of science. Next slide, please. Other skill areas contribute much more specifically to disciplinary knowledge, allowing the development of practical skills. Remember, these are just as important as the specification statements, which contribute towards the substantive knowledge. Both forms of knowledge are required for a broad and balanced science education. Next slide, please. I do feel that as a science community, we should be grateful that scientific inquiry is still considered to be an important part of disciplinary knowledge. Now, trying to teach pupils scientific ideas through scientific inquiry, the so-called discovery learning approach, is deeply unfashionable within the Department of Education. Now, that doesn't mean it is an invalid teaching pedagogy, but it does mean that it needs to be used carefully if it's going to be a successful teaching and learning strategy, especially across the full range of ability of pupils. And perhaps this is something that can be a subject of a future seminar. In terms of scientific inquiry within TWAS, what it means is that pupils need to be taught how to design and carry out experiments. And this is a feature of both GCSE and A-level work. Next slide, please. In practice, of course, there is an overlap between these three aims of science practicals. Any particular practical could be used to develop any of these three aims. One of the big ideas that we've learned in the last 10 years is that it is important that practical has a specific learning objective with clearly defined learning outcomes that we can recognize in pupils' work. And also, it's important not to have too many aims for any one practical. We're certainly not carrying out a practical in order to be able to do it, to do the chromatography practical with Smarties. Really what we're trying to do is think about what we want pupils to learn and to get out of the practical. When I show this to my students and I say, is there anything missing from these aims? They always say fun and engagement. Fun and engagement are considered to be not the aims of practical work. Fun and engagement arise when practical work is done well. They are the successful outcomes of practical work rather than the aims of practical work. Next slide, please. Now, we've already heard about Robin Miller's work on energy, and this is some more of his work on practical work. And this slide comes from the Association of Science Education. And it says that the purpose of practical work is to enable pupils to make a link between the world of objects that can be observed and measured, what they call the domain of ideas. The domain of objects and observables, and link that to the world of ideas and knowledge, what they call the domain of ideas. Or, as we now say, to link disciplinary knowledge to substantive knowledge. For this to be able to happen, for pupils to be able to use, for example, their readings of voltage and current from a circuit, to use that information to inform their understanding of electricity, then while they're doing the practical, the pupils need to be actively engaged, what Miller describes as being hands-on, minds-on. And this requires teachers to be actively involved in the management of the practical, asking questions that probe pupils' understanding, getting them to think about what the pupils are doing and why. It's not simply allowing pupils to follow a set of instructions or a recipe in some kind of mechanical way. Next slide, please. The next slide also draws on Miller's work. He's looking at why practical doesn't work. And he argues that there are two reasons why practicals fail. The first, that he calls a level 1 failure, is that pupils do not do what they're intended to do, or they do not see what they were meant to see. And this kind of failure involves errors with the method, the designed worksheet that doesn't work, the temperatures are wrong, the measuring instruments fail or inaccurate, the teacher doesn't manage the class properly, and that's what he calls the level 1 failure. And these kind of failures can be resolved at a departmental level by having regular meetings to discuss practicals, having standardized methods, standardized worksheets, standardized assessments that are tried and tested, and that the technicians know the kit that is needed and the concentrations and all of the requirements. That is an organizational thing. Level 2 failures are different. They occur when pupils do not learn or cannot show understanding of what they're intended to learn. Now, these failures can be corrected by careful monitoring and questioning of the pupils during the practical itself. And also, and this is something I emphasize very much with my student teachers, by having a full plenary after the practical, with perhaps further practice of the key ideas. I always insist that my students, if they're doing practical work, start it in the first half of the lesson, so there is plenty of time to have a proper plenary. Poorly organising a practical so you crash the plenary at the end is an unforgivable sin in my tutor group. The ideas of doing plenaries, further practice afterwards, is becoming standard practice at both GCSE and A-level core practicals. Next slide, please. One idea that is becoming rooted in science education, again highlighted in the Ofsted report, is the idea of being a novice scientist or an expert scientist. And Ofsted is arguing that expert and novice scientists approach working in science differently. The report says that experts, not only do they know more science than novices, but their knowledge is better structured and therefore more meaningful, flexible, and easier to access. And it's this expert knowledge they claim is used to solve complex scientific problems without overloading the working memory. As you know, much of the latest research in pedagogy and science teaching is focused on techniques for sequencing and chunking information so as to prevent the working memories of pupils from becoming overloaded. And indeed, in terms of practical science, we need to think about the experiences that pupils are given as being formative. They're novices moving towards being experts. It's an apprenticeship in which they're taught how to plot graphs, how to describe data, how to interpret data, how to link the data to hypotheses, how to draw conclusions. And it takes time and practice to develop these skills. And therefore, it's important that sufficient time is given across the whole of the scheme of work to allow these ideas to be embedded so that pupils can move from novices to experts. Next slide, please. So the disciplinary knowledge that is contained within TWAS can be organised into the 3 aims of practical work. And this gives us a workable framework for curriculum planning to develop knowledge across the science curriculum across the years. Next slide, please. The first step to do this would be to initiate an audit of practical work, practical opportunities across the science curriculum from 11 plus through to the end of 13 plus, using this framework as an auditing tool. And we can put this auditing tool onto the website so that you can download it and use it if you would like. The audit is designed to identify gaps where new activities need to be developed or where old activities need to be modified. Remember, we're trying to give pupils multiple opportunities to develop from novices through to the experts across these years. And at the same time, next slide please, we're given the opportunity to have a dialogue with other departments, with other subjects that develop similar ideas. This is so new knowledge can be developed in a coordinated way in terms of timing, but also in terms of approach. Next slide, please. I've taken some screenshots from the maths scheme of work and the math specimen papers here. Excuse me. The 13 plus math specification covers fractions, decimals, and percentages. Next slide, please. It also covers probability. Next slide, please. And equations. Next slide, please. And the 13 plus math specification also covers measuring, which we can then use and develop into a consideration of magnification and scale factors in biology. Next slide, please. The 13 plus math spec also covers bar charts and the handling of continuous data. And the same style of bar charts could be taught in science and in mathematics. Next slide, please. Now, there are different levels of coordination possible, ranging from timings to a comparable style and approach to shared resources or even joint activities. Next slide, please. Geography provides a perfect point of contact for a unified approach to climate change and environmental issues such as sustainability. It allows the possibility of joint fieldwork and extended project work and even EPQs. Next slide, please. Working with the English department to promote literacy and scientific literacy, possibly even looking for bespoke resources. I've got a screenshot there of a side project that I'm working on called Stories from Nowhere, which is designed to try and promote literacy and scientific thinking at the same time. And again, if you go on that website and you have a look at it and you like it, then write to me, and because I'm keen to help you or get help from people in developing it further. Next slide, please. Science has an important role to play in the development of PHSC courses within the school, especially for sex and relationships education, health and well-being, and environmental and global issues. Next slide, please. Our pupils are on journeys from novices to experts, from children to teenagers to adults, to informed citizens of the 21st century. They're growing, we would like to think, into independent thinkers, people who can do things by themselves. Along the way, they need different levels of help and support. They travel through what Vygotsky calls the zone of proximal development. Next slide, please. And we hope that the revised common entrance specifications are intended to create space and opportunities to empower you to design and build a science curriculum that is right for your school and right for your pupils. It's a long process, taking many years with constant revision, iteration and reflection. But we think it is a journey that's worth making. Thank you very much. Okay, Sophie, you're going to field some questions for us.
Well, thank you very much for that, Neil and Ian. That was wonderful. We do have some questions in the chat. One from an Ian Tinkler. I'm just going to put Barry in the convo as well. Just excuse me. There we are. Right, this is rather a long question, so I'll just whack first comment up and I'll read the full thing for all of us. So, in the energy teaching guidance, you give an example of the energy transfer from a battery to a bulb as being chemical to thermal of the lamp electrically, and then to the thermal store of the surroundings by light, and to the chemical store of the eye. This final energy transfer to the eye seems excessively complex. Would you expect students to understand this? The IOP doesn't include a chemical energy pathway in their literature. Whilst it makes sense to include this, is there a reason for the deviation? Thank you very much, Ian, for that question.
Right. Well, can I answer the last bit first? And that is the IOP doesn't include a chemical pathway. My suspicion is that it's the IOP being a bit parochial and not acknowledging chemistry, but that might be a bit mean. Others do. most other sources do include, and it's not a chemical energy pathway, it's a chemical reaction pathway. So we need to get rid of the energy part of that anyway. And so other sources, other ideas, including I think Robin Miller in his documents, do include a chemical pathway, chemical reaction pathway. And I think it's absolutely vital that we do, because otherwise, how do we explain the energy transfers in chemical reactions? I don't know if Barry wants to jump into that one at all.
Not really, but there's lots of examples. If you're just heating something with a Bunsen burner, you're transferring the energy from the chemical store through the chemical reaction to the thermal energy of what's in the beaker. So there's lots of examples.
Yeah,
I think in terms of biology, energy transferred into a living organism is going to end up in the chemical store, and that really is the key teaching point. I can't imagine ever writing a biology question about energy transfers into the eye. It's not really on the biology spec. But the idea of energy being transferred into an organism as a chemical store is very much at the heart of food chains and food webs. So therefore, I think that is something that we would want to sort of encourage that.
Well, thank you very much all.
Shall I answer the first bit, the first question as well? We put in the full pathway for from a battery to a light to the eye, really just because I was afraid that if we didn't include it, people would say, well, what happens when the light goes into the eye? And I thought it important to give that guidance so that when that pupil asks the question, there's some guidance as to how to answer it. I think I wouldn't expect to ask a question which required a pupil to put the full pathway there, particularly, but I think some will want to know and some will ask the question, and I think that's why it was in the documentation. Some pupils will understand it, most will get some of the way, and a few and some will just get the sort of input and output. So I think it depends on the pupils very much as to how much detail you feel is appropriate to go through. But the questions in the paper would expect to be fairly straightforward in terms of an energy transfer and a pathway, a simple pathway.
Wonderful. Well, thank you all three for your answers there. We do have some more questions in the chat. This is one from Peter Banks. A general question about the exams. How are they standardized? Are they standardized between subjects?
Right.
Are they standardized between years? Is a 70% in chemistry this year relatable to 70% in biology next year? How do you manage this? Thank you, Peter.
Right. Well, I'll try and answer that. The answer is we can't, because we don't see any marked scripts, and therefore we do not take the marks in from schools, so therefore we cannot do any kind of large scale statistical sampling. What we try and do is we rely on kind of our experience of setting papers, and we do have some schools very kind of sell us their results year by year by year, so we do kind of monitor that, and we can pick up rather crude trends. But the answer is that we can't do what exam boards do, because we don't mark the papers.
Okay. Well, thank you very much for that. We do have another question in the chat. Thank you all for all of these lovely questions. This is wonderful. From Myers Physics. With regard to thinking and working as a scientist, would it be possible for you to issue an ISEB glossary of scientific terms which students are expected to know? In the outgoing syllabus, the use of terminology seems to be at odds with the glossaries published by the GCSE and A-level exam boards, particularly with respect to the word reliable. Thank you, Myers.
Right. On the new ICEB website, if you go to the resources for the science curriculum page, there are a number of briefing papers that we've produced in response to teachers' reactions to the initial release of the spec. And one of them is about discussing accuracy, precision, reliability, and all of that. And that does contain a glossary at the end of that. So I think that's probably there. Whether or not we should produce something which is more broadly based on TWAS, we haven't done that yet. But again, if you felt you needed that as a resource, then write in and ask, because it is the kind of thing that we would consider doing. So the answer to that question is we've gone some way towards that. And obviously, when you're working on this spec, we want to be as transparent as possible. If you discover that there are areas of the spec that are completely unfathomable, then write and tell us, and we can produce more briefing papers to try and clarify our thinking. And we value the feedback, because it forces us to think about what it is we're trying to do.
Well, thank you all for that. We got questions coming in thick and fast. This is truly wonderful. Thank you all for submitting these. One from Emily. In the checklist comparison of the previous and new specification, forces and rotation is omitted, but is in the new ICB textbooks we have just bought. Is there a reason for this?
Yes, the new ICEB textbook which you've just bought is covering both Common Entrance and Key Stage 3, and therefore there will be material in that textbook which is not assessed at Common Entrance.
Wonderful.
And that was an editorial decision taken by the publishers.
It might be worth saying that forces, of course, is in the new Common Entrance specification, but rotation, as in moments, is not, has been removed from the new Common Entrance specification.
Thank you. Myers Physics has just written in with thank you. What is the best contact details to get in touch with all of you if you're happy to
contact us through ICEB. What's the email address, Sophie?
For us, it's cpd@iseb.co.uk.
Yeah, something like that. That is the best way to contact us. We're in regular contact with ICEB High Command and can respond as quickly as we possibly can. As I say, we're not trying to make anything obscure and difficult. What we're trying to do is clarify. We clarify the way our thinking is developing, really.
Well, thank you very much. Sorry, I've just been locked out of the chat. But we do have a couple of pre-submitted questions whilst I just log myself back in. This is one that we had through our emails. I'm just going to pop it up on the screen now. In CE Science, the new model of energy, page 3, it states that the pathways we shall use in Common Entrance are electrical, light, sound, and chemical reaction. The mechanical pathway is not listed. Does this mean that the mechanical pathway will not be examined despite being taught?
Shall I jump in there?
Yes, please.
Yes, to be honest, that is an error. Thank you for pointing that out. And I hadn't really spotted that it wasn't specifically listed there. It should really say mechanical and then give examples of sound and water waves, or sort of including sound and water waves, and that will be amended in a future edition of the document. It's interesting that on the same page it does actually go into some detail about mechanical pathways. Now, at some stage, I'm sure, once the document has been amended, we will examine mechanical pathways, or hope that people will talk about mechanical pathways. But we will be aware of the fact that the first edition of that document didn't actually specifically list it as one of the pathways.
Well, it said sound brackets mechanical, and it should have said mechanical brackets, e.g. sound and water waves, shouldn't it? And that's what we
Yes.
directed it to. So that was really just a typo that we'd missed. The specification says energy pathways brackets such as, and doesn't specifically list them. Now that means that we would not ask a direct recall question on the names of those pathways, because they're not actually named in the spec, except the ones that are mentioned. I think that's the key point there. But there's nothing to stop us in introducing the idea as part of a question and then expecting students to use that information.
Wonderful. Well, thank you, three, for that. This is one from Nick Chapman. I was taught around 10 years ago by IOP that vibrational energy stores included light and sound. I noticed that you have not included this. Has there been an update to recommendations? Thank you.
Well, I'm afraid there is not universal agreement between everybody's descriptions of the pathways. I think if you read the best article, which is referenced in the energy document, which on the ICEB website, you will see that they say that some sources use the idea of vibrational pathways, but we have decided not to include these, and I think sensibly so. And as a result, for one of that reason, we didn't include it either. I think it adds further complication, which isn't necessary, because essentially a vibrational pathway is usually a mechanical pathway, or often a mechanical pathway. So I think we decided to not to mention vibrational pathways at all. So you can think about it if you like, but we certainly will not refer to a vibrational pathway in any question, in any CE question. And I think it adds a further complication which we don't need to go into at this stage.
Well, thank you very much. We have a comment from Kelly Archer here. With regards to Peter's question and your response, I would happily share either a sample of marked scripts or an analysis of which questions were challenging for future use. Thank you, Kelly.
We would welcome that. We would welcome anonymized marks. We would welcome any comments about specific papers. One or two schools do this already, and we look at them. We are quite reflective on what we're doing, and we are trying to make papers that work. And therefore, obviously, if you find that, I realize you're all very busy, but if you can find the time to do this, then we will certainly take what you say seriously.
Well, thank you very much. Just have another few questions from Emily Castley. Will the new spec papers be sat from November 2022?
Yes.
The November 2022 paper, I understand, is a specimen paper that isn't actually examined in live exams take place in January in the summer. That's right, isn't it? But yes, the November 2022 paper will be along the new spec. Yeah.
Wonderful. Another question from Emily. Will LED and LDRs be examined in the new specification?
Yes, I see no reason why not. Yeah, they can certainly be used in circuits, and it will be expected that students, pupils, will have had experience of using them.
Lovely. Another very good question from Joe Rolls in the chat. Pupils that take level 1 often have extra time for exams, which can lead to the exam being 1.25 to 1.5 hours long. In the future, could level 1 papers be prepared for the 3 sciences?
Are you asking for the exams to be sat on 3 different occasions in the same way that the L2 papers are? Is that the question that's here? Or are you asking for the questions within the paper to be organized into section chemistry, biology, and physics?
Do write into the chat, Joe, and clarify your question. And we can offer an answer.
regarding the first one, having 3 separate shorter papers, yeah, thank you, Joe. That is something that has been discussed. And it is something that we would consider. Okay, the L1 papers are produced completely separately to L2 as a separate writing team, and I think one of the things I'm most proud of, I think, is the quality of the L1 papers, because I think they're excellent. If we felt that there was sufficient groundswell to allow this to happen, then we would certainly consider that. And so therefore, if you feel it's important, then write and tell us. I think we need to see how the new spec is bedding in, because again, one of the things that I was reluctant to do when we launched the new spec was to change the exams at the same time. I felt if I changed both the spec and the exams at the same time, that would make life very, very difficult for schools. So we intentionally haven't changed the examinations, and therefore, but that is something that we would be willing and prepared to review.
Well, thank you very much, Joe. Ian Tinkler is back. Thank you very much, Ian. I would also welcome this. Additionally, the level 1 papers have a very high expectation in terms of knowledge recall, very specific knowledge. Whilst AO1 is the easiest strand, many pupils can't cope.
Well, that's very helpful. Again, I'm very grateful for that comment. That's something that I would take back. We're having a meeting of the science examining team leaders early in July, and if Sophie can wrap these comments up for us, I'm happy to present them to the team. Although 2 of the team are already here, so they already hear them. But the L1 papers setters can hear that, and that's something we can talk about. No one has said anything about 11 plus at this point. Would the same point be made at 11 plus? That 11 plus papers have a high expectation in terms of knowledge and recall?
While we wait for the answers for this question to trickle in, we've got another one from Peter Banks. And by the way, thank you everyone for submitting these questions. This is absolutely wonderful and completely what we wanted from these sessions. We're very keen to have all the feedback we can get from schools and teachers, so thank you very much indeed. As a director of studies, I often use the single level 1 papers to help alleviate pupil exam pressures where needed. Sometimes pupils need more space in their schedule.
Yeah, I can see that. Are you saying, Peter? Are you saying that you are encouraging pupils to take the foundation L1 paper in preference to the L2? Because again, that's something that we would. Right. Okay. So you're saying that your children do not formally sit 11 plus for their future schools. Right. I understand. Right. So again, that's something that I'm happy to take back and to discuss. My understanding is, and again, I'm grateful for correction on this, is that the decision to whether or not a pupil does L1 or L2 is not really taken by the science department. It's much more taken by the director of studies in conversation with the senior school and the parents. So again, that's something. If that is so, then that's something that we would need to look at. Yeah. It's a very busy week, says Peter. Yeah, I appreciate that.
Well, thank you all for your time in attending these sessions. It's very kind of you.
No, I think he means it was a very busy week for the pupils doing the exams. But yeah.
I know, I realise. I'm grateful for everyone's attention on this.
But it's very busy for him as well, I suspect.
We have another pre-submitted question. I will have to ask that we wrap this session up because we're just over an hour. That's wonderful. So if anyone has any further questions, please put them in the chat and we'll get to them just after this one previously submitted question. Thank you all very much. Do we still teach energy transfer diagrams with stores represented as boxes and pathways indicated over arrows? And that's on visual representation of stores and pathways.
I think we could. I can't see any reason for not doing so. We could have a box for an energy store and a pathway and ask pupils to name a pathway, it seems a legitimate, to me, it seems a legitimate way of asking a question on energy stores and energy transfers there. So I think I see no reason for not doing so. What you wouldn't do is have a box in the middle, which was specifically a form of energy, which was the light or the sound or whatever. That we would certainly change, and we would make sure that it was clear that it should be an energy pathway rather than that. And I think we would indicate the pathway as an arrow. Yeah.
Wonderful, thank you very much. Another question from Peter here. As general, more than science. Why have the level names changed? Level 1 and 2 is easy to explain. We now have foundation and level 2 in science, foundation core and additional in maths, and levels 1, 2, and 3 in Latin.
I don't know why the names were changed. I think you're making quite an important point here, which is that there needs to be some kind of comparability across all of the subjects. And again, that's something, having mentioned that to us, that's something I'll take back to and we can think about. They used to be called L1 and L2. Now they got called Foundation. I don't quite know why the names were changed. I think it was to bring it in line with maths, but I'm not sure.
Well, thank you very much, Peter. If anyone else has any questions they'd like to submit to the chat for our science experts, please do so quite quickly, because I would like to wrap the session up. I think I'm very, very grateful for all this wonderful engagement, and we will, as Neil says, take all of these comments back to our setters meeting. So thank you very much indeed. Please do write in, and if we don't get to answer your questions, to cpd@iseb.co.uk. I will respond to every message I receive. No, thank you.
Thank you, Peter. We will.
Thank you very much. No, we will take all of this back, and we will all give it all due consideration. Thank you very much indeed.
I always feel it's a good CPD when I come away and feel I've learned something, and I felt I've learned something tonight. So thank you all very much for the time and effort you've spent in doing this.
Oh, and just for to answer your question, Joe, yes, each session is recorded, and every registered attendee will receive both a recording of the webinar and slides used in the presentation as soon as we can after the event finishes. It might take up to 2 to 3 weeks, but you will definitely have it. And thank you all very much for attending.
Thank you. Yeah.
Thank you.
Thank you. Have a wonderful evening.
Yeah. Bye, everybody.
Cheerio.
Well,